Hi, I'm Robert. I'm working for SAP since 4 years, but I'm not here in the name of my employer. I'm here because I like C++ and because I don't like the environments essentially you have to deal with. So I containerize my stuff so that I don't have to deal with it too much. This talk doesn't really have a clear structure yet. I gave talks about containerization before, and I hope I can take some parts out of there and add some more interesting stuff that I learned over the last couple of weeks. But to get like a picture where this talk should be going, could you please answer a couple of questions, like who's familiar with Docker, for example? Oh, that's almost everyone. Okay, who's familiar with Linux namespaces? Ooh, fewer hands. Okay. So, what else? Who's familiar with Kubernetes, for example? Okay, makes sense. Only a couple, like 3-4 people. So, who knows LXC, Linux containers? No one. Okay, Podman, maybe. Okay. These are other containerization tools, so to speak. Yes, Docker is all the hype. That I think also shows in the vote here that basically most of the people here know Docker. But I don't want to talk specifically about Docker here. There are lots of tutorials already about Docker, how to get into it, how to use it, and so on. I'm also certainly not a Docker expert or a containerization expert. I would consider myself as a user of containerization, and I'd like to normally get a bit deeper into things and get some more understanding. That still does not make me an expert on anything here. So if you want to share something, then please raise your hand or raise your voice. And so we can have an exchange of information more than just me presenting things. Okay, containerization. What is containerization? Maybe someone of you can explain to me what containerization is, because I have my point of view on it, there might be other point of views. And recently I'm like struggling more to differentiate between what is containerization opposed to other things. So can someone here maybe give me one definition of containerization? Yes, please. Like a lightweight virtual machine. Okay. So maybe a different way of defining containerization? Yes? A full set of user space dependency under the control of the developer. Okay. So we have dependencies in here and that we have control over it. Okay, maybe. Sorry? Not the kernel space. So we have control in a container over the user space, but not over the kernel space. Okay? Maybe some other ideas of what containerization means to you? Yes?
More isolation than processes give us.
More isolation than processes?
Like virtual machines give us.
But less than virtual machines. Okay, there were some other hands there. Change root on steroids. That's interesting. Yeah, I also agree with that in a way, yeah. Certainly, yeah.
And constructing images one on top of another.
Constructing images on top, one of another? I'm repeating the question so it's in the recording. The answer, sorry. They are ephemeral, so they're ephemeral? Okay. And you can start them again from scratch. Okay, that also kind of ties to the we have control over it and isolate it, yeah.
Specific ways, which is very useful.
Yeah, specific control, yeah. Okay, and there was another hand back there somewhere? No? Okay. So, yes, I also have the impression that Docker is, not Docker, sorry, that's what I don't want to talk about today. Containerization is these kinds of things. But what I specifically got confused about recently is the difference between containerization and virtual machines from a using point of view. From a conceptual point of view, we know that there is a clear distinction. The clear distinction is that virtual machines run with their own kernel of the operating system, whereas containers do not run with their own distinct kernel. They share the kernel of their host. So, can draw some boxes if we have some chalk. So you have a host, whatever that is, that can be a virtual machine or a physical machine, and it runs a kernel somewhere. That's maybe a bit too small. So we have a kernel somewhere, and then we have the containers, but they all run on top of the same kernel. Can you see this if I draw it here? Otherwise I will draw it here. Whereas with the virtual machines, I have some kind of host on which I have a kernel, which includes an hypervisor or is linked to a hypervisor. Normally there's a kernel module on Linux for that. And then I have the virtual machine, which has its own kernel that then talks to the hypervisor, and via the hypervisor to the kernel, something like this. And if I have another virtual machine, it also has another kernel that then talks to the hypervisor. So the distinction between those, from a conceptual point of view, is virtual machines have a separate kernel with then separate kernel resources. But these things can also be nested. So you can have a container which manages a virtual machine, but it still has to talk to that kernel. Or you can have a virtual machine inside of which you can have a container. So the most prominent distinction from a usage point of view that you can find when you look just for a difference between containers and containers and virtual machines, sorry, is that containers are supposed to be lightweight. They solve a there are already people laughing about this. So the problems they solve have an overlap, and in this overlap, containers are supposed to be more lightweight. They're supposed to consume less resources. They're supposed to consume less CPU. But you can optimize. You can optimize virtual machines, and of course there are people who have interest in that. For example, Intel, who wants to sell their hardware, so they want to make their hardware extensions like virtual machine extensions, accelerations. They want to sell this, and for this they've of course tried to find applications. And virtual machine is a good application. If you can replace a container with a lightweight virtual machine, that's a selling point for their special hardware. So they brought it down to, I don't quite remember the exact numbers, something like 150 milliseconds to boot a virtual machine, and a RAM overhead of something like 20 megabyte maybe. And in the order of things, if you look, for example, at the startup times of a Docker container, or even of a Kubernetes pod, 150 milliseconds is nothing. Normally it takes on the order of seconds or even much longer for the application that's inside of the container to spin up. So from a performance point of view, you could argue that you can use virtual machines. You don't have to use containers. So it mostly boils down to usage point of view. Where's my ecosystem the better one currently? That's, I think, the current distinction you have. You have Docker, you have huge support of Docker currently, and they're focusing on containerization. And similarly, Kubernetes, it has different ways of running their applications inside, and one of which is Docker. And this also has the best support because it's the most widespread. But you should keep in mind that with optimizations, you can also use virtual machines. Now, why is that important? Because we have a shared kernel here and shared kernel resources, we also have a shared attack surface. You can basically try to attack one container, then attack the kernel, and then gain access to another container. So whereas here, you first have to attack the kernel, and then the hypervisor, and then the other kernel to get to the other VM. And that is normally more difficult, because the link between the kernel here and the hypervisor is very simple, or relatively simple. And so VMs are well understood, and they are considered as more secure. This is not a question about what we're talking about when we talk about containers. If we're talking about the ecosystem around it, yes, you could use the ecosystem to build virtual machines. But the fundamental concepts of containerization on Linux are such that we isolate processes. And because we isolate processes, that only basically makes sense if you have a shared kernel. Otherwise, why would you isolate the process? So if you take the kernel with the process, then you have basically a virtual machine. There's also something that is called Linux in user space, which you know relatively little about. So you could run theoretically a kernel in user space without having a virtual machine, but I doubt that this performs well, to be honest. So regarding hardware support, what's usually there is, for example, that you don't emulate the CPU. Instead, your CPU has support for additional virtual machines, where you then separate privilege levels. So the privilege level that this kernel gets is a different privilege level from this kernel of the hypervisor. And then there's also support for splitting the RAM, for example, such that this virtual machine cannot access the RAM of this virtual machine or the RAM of those virtual machines. What is important to note besides security is a performance concern regarding I/O. So we know that we have pretty good support for virtualization when it comes to CPUs and RAM. That is relatively fast, or pretty much native speed. But there is a thing to be said about I/O performance. So performance when it comes to disk access and network, which are, I think, the two most important parts when it comes to cloud. There's also GPU, but it has similar issues. When you run a virtual machine naively, so to speak, you would emulate a disk drive, for example, which then has to be backed by some storage that comes from the host. And this would be slow, because first you have to talk to this virtual device here, and then through the hypervisor in a non-optimized way to some storage here on the host. Traditionally, for example, if you use something like QEMU or VirtualBox or VMware, you have these. You have a disk on here somewhere, which has a file that contains the disk or the data for the disk that is used inside of here. So basically, you have to go through this kernel, through the hypervisor, through the file system to read or write data in here if you're doing disk I/O. And this is not necessarily fast. What you can do instead is you can get further hardware support to accelerate this again. So for example, what you can do is you can take devices from the host, like an entire disk, and forward it to the virtual machine. So that doesn't have to deal with the file system, and it can talk more or less directly to, I think it's still going through the hypervisor, I believe. You can, for example, talk to some controller, some PCI controller, or to some disk directly. So what this means is, in virtual machines, you typically have some performance downside when it comes to I/O, but you can again try to optimize this. So you start off with low performance, and then you try to gain more performance by using specialized hardware, for example, or specialized configurations. Whereas with containers, you start off with basically native performance, and you try to secure them. And that's usually not something that you do, but something that your containerization framework does for you. Okay, but enough about virtual machines. The point is, you can use them. They usually get you a more likelihood of being secure, at least the security between different virtual machines. But then you have to take care of performance and start optimizing stuff. Okay, if I may interject some current situation from my enterprise background, I have heard about several situations in which people or customers, for example, do not want to run different applications on top of the same kernel. So where they're basically enforcing multiple virtual machines. And this is likely to get some better integration into things like Kubernetes in the future. That's what I guess will happen. Just because of, for example, there are standards to uphold in certain industries, where they then require that an application must not run next to another application if it's for a different customer or for a different purpose. So you would probably need this separation into virtual machines. I already know of some open source projects, I don't quite remember the names of them, where this was combined. So the containerization aspect was combined with Kubernetes, was combined with virtual machines to get the best security while still maintaining the same ecosystem. So we'll see mixtures of this in the future, I guess. Okay, but now to containers. So I have very little experience with iSCSI. The ones I had were not good because It was not a well-maintained product, so to speak. I think it was Ceph, and it has an iSCSI gateway, and it didn't really work well. So I cannot really make a comment on the performance there. But yes, what is typically done, for example, in Kubernetes, is that you attach persistent volumes to containers, so that you can have stateful applications, and these persistent volumes are something like remotely attached pseudo block devices, so something like a Ceph Rados block device. So there are, I guess, several aspects to this. First of all, yes, since you're using the same kernel from different containers, there are shared kernel resources, and this has an impact on performance. Certainly you cannot just ignore the other applications that are running on this if you really want to fine-tune performance, because there are things which are not yet well isolated within the kernel itself. I guess the scheduling might be part of it. What was the other aspect? The other aspect is, of course, there are developments currently, for example, the control groups, which are already old, and I believe that they will just expand. So control groups are something that I not have deeply looked into, but they are part of this containerization thing. What they're mostly being used for in containerization is to say that this container is only allowed to take up a certain part of the CPU time. So you get, for example, a quota of 25% of the CPU time this container can spend. Similarly, with control groups, you can also say that this container is allowed to have 2 gigs of RAM usage. And if it exceeds this amount of RAM use or tries to exceed this amount of RAM usage, it's being killed. This is part of this isolation aspect, where you of course need some guarantees that this container is not starving other containers, otherwise you will definitely see these effects. And what you're trying to do is you're trying to isolate such that each container can run on wherever it is, because there's a guarantee of getting enough resources not to starve. So, and maybe in the future there will also be more control groups that then, or fine-tuning to control groups that prevent this kind of starvation if an application is not well behaved. Okay, I would like to share some of my what I've found essentially about the basics of containers. And I do this, or I like to do this in the form of demos, because I like them personally. So hopefully you can also take something from them. Normally when you want to discuss this in detail, would actually have to go and look at the system calls involved, because this containerization, at least on Linux, is a set of kernel features that are interacting, and that is also where some of the complexity arises when you want to deeply understand what containerization means in Linux. However, I think that this is too much of a hassle to write a C program for this, because there's too much of the details in there, too much of the stuff that you have to take care of, and error handling and so on. So I like to do this on the shell, which is somewhere in between Docker, for example, as a super high level application, and writing C program that does things. So chroot on steroids was made as an example of what containerization is. I like this because this is also where I start normally with his demos. So let's see, I have documents, and there's the container CPP. Okay. So in here I have a busybox. Let's look up what this busybox is. Is it a statically linked or not? It's not a dynamically linked busybox. That's good. So inside of this folder, let's just hide a bit and make this a bit more. So inside this folder I have a busybox. Busybox is a shell that is meant for embedded use, or use where you have little space and little configuration. It is usually compiled as a static binary, so it has no dependencies, and it includes not just a shell, but a host of other tools. So let's see. We can run busybox sh, and we get a shell. Now I have this shell. That's why my prompt now changes, because now it's the prompt from busybox. But I can also run busybox and say busybox ls to get a list of my current directory. And similarly, I can run busybox mount to get the mount command. These are all built-ins into busybox, which will become important in a second, but just for understanding what this binary is and does. So it's used for embedded systems also during the boot sequence, just because it contains basically all necessary tools you normally need. So when I, for example, run mount, it might be a binary that resides somewhere else, and I have to have this binary and another binary and a third binary, and have to set up an entire system. Sorry? Ah, yeah, and this, not entirely sure. I'm not entirely sure about the built-ins of busybox, but the busybox that I normally find, they don't have built-ins. That's kind of strange. So they're trying to run executables even for something like ls. That's, yeah, it's... Okay, yeah, some but not all of these are built in. But the rest you can access via the busybox executable and then passing the name of what you want to do instead. So anyway, this is busybox. Now, I can isolate busybox from the rest of the file system by using chroot. Chroot stands for change root, and it kind of fakes where the root of the file system is. In Linux or in Unix, where this entire thing comes from, we have a file system hierarchy with a single root, as opposed to Windows, where you have the file system drive, so which you can access with the different drive letters. Every drive has its own root, so C, D, and so on, and there's not really a super root normally if you use normal paths, for example. But under Linux or Unix, you have a single root, and then everything else is under that single root. What chroot does now is, for the process which runs under this changed root, it appears as if the directory that I specify is the root of the file system. So let's make it like so. I change root to here, and I have to run then a process which is inside of this. Typing like this is a bit uncomfortable. That doesn't work, then I'd use the other keyboard. Alright, so, and I'm out of the busybox again because I have to run busybox sh to get a shell. Now, I have a shell which runs under this changed root. And I can see this by running busybox find on slash. So show me everything that's here. That's not very instructive, so let's run an ls on slash. So now my root directory is the directory in which I've been before, to which I changed rooted. But chroot is not great because the specification of chroot allows a root user to break out of the chroot. That is a property that is more widespread in containerization. With virtual machines, once you start a new kernel, you're totally isolated from the host. You have to set up the links to the host again. Like, for example, if you want to access a file on the host, you have to specifically set this up, set something up in the kernel here, set a connection up here, have a driver for this in the kernel inside, and so on. With containers, it's the other way around, at least in the implementation on Linux. By default, you have access to everything, and then you restrict the access further and further. And if you make a mistake there, you have a potential security issue. And this is true for chroot, but it's also true for the mechanisms that are actually used for containerizations. If you have a way to access a file outside of your container, you can access that file. And with proper permissions, you are able to modify that file. And similarly with chroot, if you have access to a file outside of the change root, then you can operate on that file. And even worse, if you have access to a directory outside of the change root, you can change root to it. So you can break out of the change root by being the change root, having access to a directory outside, and then change routing outside. And that is unfortunately surprisingly simple. Unfortunately, it needs a C program. I don't think I can do this in shell. So I will not demonstrate it now, but you can easily find this. For change root, the point is that you take a file script or a handle on the current directory, you create a temporary directory. Since you're root, you're allowed to change root into this temporary directory, Now you have a file handle on a directory that is outside of the change root, and now you can just prepend // here to get to the parent directories there. That is a quirk of the implementation of chroot, and I hear that it's better in the BSDs. But yeah, change root is not used in common containerization tools. But what I see was interesting. There is a project called Bocker, so a Bocker with a B, which is Docker implemented in 100 lines of Bash. It's interesting. I will do something similar here, but it's using change root, which means that it's practically useless. Okay, but since we are in this change root anyway, there is something else to talk about. And what I want to talk about now is the pseudo file systems, or the virtual file systems of Linux. There are two, or there are several ones, but two important ones, which are the proc file system and the sys file system. The proc file system contains information about the current processes. And you use this, for example, to get information about your own process, how much memory consumes. You can also use it to communicate with other processes in certain ways. And the other file system, virtual file system, is the sys file system, which contains kernel tunables. Since I change rooted here, my current busybox process does not have access to those file systems because they're normally under /proc, so directly in the root, and /sys also directly in the root. And here I cannot see them. What I can do is I can run busybox mkdir proc to create a directory called proc, and then I can run a busybox mount to get a mount command, and now I can mount the virtual file system. -t proc none proc. So, and now I have busybox ls proc. Now I have access to this proc file system, and the numbers you see here are the process IDs of the processes running on this machine, which also shows that this isolation is far from complete. So just change routing is certainly not sufficient for any isolation. Normally what you do is you combine change root with a user switch. So change root itself needs root permissions, but then inside of this change root environment you drop your root rights and become another user, and that other user then does not have change root rights. That other user cannot mount things. That other user cannot simply do any kernel tunables or whatever. So this is how things have been done for web servers, for example, for a long time. So change root is old. Yeah. Proc mem or something like this. Is it here? Proc mem info proc. I don't know it to be the case. Kmem. KMSG. It's disabled. It seems to be disabled here, but yeah. So. Yeah. Okay, so we have to do something like this, which we cannot. So in theory, I could change my user ID in here. The problem is I have no. I don't. The problem is I think Sue tries to log in. So I could, with a kernel call, change my user ID inside of here and then achieve the necessary isolation that I want. Unfortunately, I have no tool for this here unless I compile a C program, because busybox only comes, I think, with Sue. Sue is a login tool, so I have to create then a user entry for this login tool to use to log in. But yeah, let's not talk about change roots anymore. Let's talk about how things are actually done. How things are actually done is a bit more complicated, but first let's sudo mount proc. So what I will do is the following: sudo mount --bind dot to proc. So a bind mount is something like a symbolic link, in that it takes a part of the directory of the file system tree and also makes it as accessible under a different folder or a different path. So now I have two ways of referring to this folder. The one is this. Yeah, and the other one is cd proc pwd this. So that's a bit strange because I now hung the entire file system tree under itself, but it's just I take essentially a entire part of file system tree and make it also accessible somewhere else. Why is this necessary? This is necessary because I need a mount point now. And with the mount point I can do something that I cannot demonstrate right now, but I will demonstrate in a second, and that is to change the root for everyone to a certain folder, a certain mount point more specifically. With change root I only change a property of a certain process. With a syscall called, I think, pivot root, it's called, I change the root of the file system for all processes. And this is then secure because I have no way of referring to this other outside stuff. It's more secure, but still not entirely secure. This is what actually used in containerization. But why can't I kind of demonstrate it now? Because if I were to do this, I kind of have to reboot. Because I cannot access anything outside. I would have to restore my system, and this is kind of messy. So, we would actually like to change the root for all the processes inside of the container, but not for any processes outside. And that's where one of the isolation comes in. This is called a mount namespace. And this namespace thing to me is confusing because I'm a C++ guy. Namespaces for me mean something different. What they're talking here is about isolation. And this mount isolation means I create a container inside of which I can manipulate mounts and also the root without affecting anything else on the system. And because we do this kind of in a transitive way, we can define a root mount namespace. So this is the normal thing that you're in when you don't have any containers or whatever. You are in the root mount namespace. Then you can create a mount namespace. Inside of this mount namespace you can do arbitrary mount operations that are invisible to the outside, and you can also change the root of the file system for all processes that are living with this mount namespace.
That kind of reminds me of Windows drive letters.
Yeah, something like that, but I believe you still have a shared root that is pointing to here. So the mount operations that you do in here have to refer to stuff in here. So it's still kind of one root. Okay. Yes, and then you manipulate. I will demonstrate it. Hopefully I will not screw up my machine. So to create a new mount namespace, there is this shell tool called unshare. I have to run it here as a root for now. -- mount, and this will start a new process. By default it's the shell, so it will start a new shell. And this new shell will live inside of a new mount namespace. How can I prove it? Let's do it the following way. Sudo eu mount proc. Where am I? pwd, I'm here. Sudo eu mount pwd proc. Okay. Sudo unshare -- mount. So now we do the following. We do again a sudo where root, so mount -- bind dot to proc. So okay, now mount. Oh Jesus, where do I have the pipe character? US keyboard layout, UK keyboard layout. One key more. Grab proc. So I'm running now a shell process that is inside of the new mount namespace. I created a new shell process implicitly in I'll use my finger, that's easier. I create a new shell process here implicitly, because unshare starts a new process by default, that's a shell. And I'm using that shell process for all the commands below, that's why also the prompt changed. Inside of this mount namespace, I now performed a new mount operation, a bind mount. And I bound the dot folder to proc. And I can see this if I just display the current mounts. That I have two mounts that are called proc. One is actually the virtual file system on /proc. And then I have some systemd stuff, whatever. And I have a bind mount here, this thing. That's the bind mount. It doesn't really look like a bind mount, but this is the one that I performed. So now, let's compare this to what I can see in the root mount namespace. If I can... so now I have opened a new shell. This new shell here lives outside of the mount namespace. It lives in the root mount namespace. I can do the same. I can do mount, and then I do pipe, and then I do grep for proc. And there is one entry less, because the bind mount that I performed in the new mount namespace above is only visible in this new mount namespace, but not on the root mount namespace. Okay, so I have this isolation, and now that I know that I'm isolated, I can perform pivot root dot dot, and I have to look up pivot. I think you specify a process that... Nope, we don't have to. Pivot root dot dot. So, and now I have to be careful, because the bash that I'm running is still running, but it has no way to access any files, because I now changed where the root of the file system is. So what I can do is I can run busybox, and I basically exec it because I don't need this bash anymore. Busybox. That was stupid. Because by just running busybox I got the help, but not the shell. And the help exits, and then my bash exits, and now also the mount namespace is gone. So I have to do this entire thing again. Okay, let's see, mount. It did exit. I'm with a different prompt now. It exec, and then busybox exited. So to explain this for people not very familiar with Unix, what exec does is takes the current process and runs a different program under the current process. So it has the same process ID, and if this new program exits, then my process is gone.
The last process exits, which has access to the namespace, is this namespace that is destroyed?
Exactly, yeah. So with the namespace, not just with the mount namespace, but also with other namespaces, they're usually bound to processes. You can extend their lifetime via bind mounts, but normally they're tied to processes. So when the last process who participates in this namespace exits, it's gone.
Do namespaces have names?
I don't think so. You can give them names by mounting them somewhere, but I mean, some tools refer to namespace names, but what they mean is then convention in their own tool, and not to a general name of the namespace. Mount minus bind dot to proc. I do the pivot root again. Pivot root actually moves the root of the file system, the current root of the file system, to one folder, and then another folder to the root of the file system. But what I want to do is I want to move the root of the file system somewhere else, and that's why I have to specify two arguments here, which are the same. And both mean refer to the current folder, so I'm using the current folder both as a target for the old folder and as the new root. It's strange, but it works. Yes. Not quite. What they use as a different tool, so from a syscall point of view, this thing is used, but they use a tool called switch root. I will maybe explain later on, but first I need to do this. Yeah, I need to go to proc, and then I need to go to pivot root, and then I need to exec busybox sh. And now I have a shell. Busybox ls /. Okay, now same effect as with chroot, but I cannot break out of this by change routing, because it's a different mechanism. Yes, I can. But this is the problem. So busybox mkdir actual proc busybox mount -t proc none to actual proc, and then I can actually do a busybox cut actual proc mounts. Lots of things still there. Huh?
Does busybox use the private variable?
I don't know. Probably. I mean, if I unset path, I can do an ls. No. Okay, so I can.
You mounted, yeah, you have mounted your SDA 2 times on slash.
Yes.
With different root directories.
Yeah, so this is the second one here. That's a bind mount. That's a bind mount of into this proc folder, which does not show up as a bind mount here, but okay. Yeah, there's still lots of stuff that I should actually not be able to see, but yeah. So let's talk quickly about the switch root thing, because I thought this was also quite interesting. When you boot up your machine, this is a side, we're sidetracking here. It's probably not good, but I like this too much. When you're booting up your Linux machine, what normally happens is you load 2 things into RAM. One is the kernel, and another part is the initial RAM. Oh, it's not really RAM disk, but it has this old name init.rd. This thing here is not quite a file system, but it's a list of files like a zip archive or a tar archive. And it contains tools and kernel modules. And the idea behind this is that you have a disk which can have an arbitrary file system, and it can be on an arbitrary drive, and you need something for the kernel to load stuff from here. And you also need to tell the kernel where this thing is. And this is part of the configuration stuff and the tools that reside in here, in this initial RAM disk, which is not a disk anymore, but okay. So what happens is that you load this, the bootloader loads these 2 into memory, into main memory, and then starts the kernel. The kernel unpacks this into the tempfs, yeah, it unpacks it basically, so it has access to these files. And then, after it's unpacked it, it sets the root to this virtual file system, to this RAM-backed file system basically. And then it runs here the /init process. So the /init process sets up the system, like it performs the mounts, it knows then where your disk, for example, is in your home directory and whatever. And after it set up these mounts, it then has to switch basically from this temporary file system over to your disk file system, so that your root later resides on the actual disk. And this is also done with the same syscall pivot root, but it's done with a tool called switch root, which removes all of these things because you don't no longer need it and they consume space in RAM. And coordinating these tasks is apparently tricky because you end up with no executables anymore after you've deleted everything. So it's done in one. But anyway, that's about pivot root and switch root. So you see this tooling originally, I think that comes not from containerization, but it comes from the initialization process or in the boot process. But it's just trivia. Okay, so we have isolated this process somewhat. It's not perfect because we're still root inside. Because we're root inside, we can mount the dev file system, and from the dev file system we have access to the disk, and then we can mount just the entire disk again inside, and we can see it. Or you can create a device node, yes. I normally don't do this anymore, but yeah. So, it's still not the perfect isolation, but it's like a first step. But I would like to step back a bit and now talk about the other namespaces there are. So, in Linux, as I said, you don't have one way of isolating a process. You have different sets of features that are each isolating one part of the process. Mount namespace is one of them, but there are, like, I think 5 in total. The root of all the evil is the user namespace. This isolates privileges and user IDs. Then we have the mount namespace. We have the process ID namespace, such that you don't see other processes anymore. And you have the network namespace. This is for isolating network devices, the TCP IP stack of the kernel, and firewall rules. And then there are some other ones like, what is this called? The UPS, yes, it's for hostname. UTS, yeah, UTS. It's for the hostname. I'm not sure if there's something else. A system time also for... Okay. And there's the IPC namespace. Okay. So why did I call the user namespace the root of all these things? When you use Docker currently, you will not use Docker. No, you will not use user namespaces. User namespaces are tricky, but the other namespaces derive their their permissions from the user namespace. By default, you're using the root user namespace because we kind of make this transitive to be simple, like there is a root for everything. But I will talk about user namespaces in a second because I think they're important and they're also interesting. The PID namespace, you normally get this, for example, in Docker, and you only see the processes then they're actually run inside of this PID namespace. When you look at the proc file system, you will only see, for example, entries for processes inside of here, and they will also start with the PID 1, and not some arbitrary 10,000 number or something like this. So the first process enters the PID namespace will get PID number 1. The mount namespace we have already seen. The network namespace is also interesting. The network namespace allows us to isolate, from a network point of view, processes from each other, but also to let them again then talk each other, link them together. And what I find quite interesting is that you can do the following. Many applications are written in such a way that they only allow one user on a port. Like, for example, port 80 for HTTP servers. And they're then run exclusively, so you cannot start another program that also listens on port 80. Now, what do you want? What will you do when you want to run, for example, two Nginx or Nginx and an Apache web server on your machine? Both want to listen on port 80. You have to configure them, and that's the pain. This is one of the things that whatever solution you use, virtualization or containerization, one of the big advantages of this over developing an application and configuring it is they can hard bake a lot of the configuration. You don't have to specify where files live, because files are part of the container. The paths are part of the container. Everything can be hard-coded in there. Similarly with port numbers and addresses. You can just, inside of the container, listen on all available interfaces, potentially all available ports, but you can just hard-code the port, and then link the container to the outside world in a way that limits its reach. So all the interfaces in here basically then go to one interface in here, and all the ports in here you only allow outside communication via one specific port, for example. And you can also remap that port to another port. You could also do this without containerization, but then you need configuration again. You need to, for each program specifically, to tell it back how to behave. And when you go back now to Docker, for example, Docker integrates all of this stuff. In the end, in Docker you don't say, please make me interface here and route it to this port and so on. No, you just say, publish port 80 here on port 1, 2, 3, 4 on the outside. And it takes care of dealing with this entire setup and configuration of the container, networking, and how this is connected to the host. By the way, similarly with other containerization solutions, so Podman is also a containerization solution. I haven't looked at the implementation, but I also fear that something like this is the case. So we know from, for example, the usages just of containerization alone, that there can be these kinds of leaks. For example, for this mount namespace thing, as I said, if you have a file descriptor to the outside of the mount namespace, you can still access this. And this was an issue in basically all containerization solutions, where the process which started this entire thing was still accessible via the proc file system. So it was something like proc1, it's the file descriptor that refers to the running process. And via this file descriptor, you could then overwrite the initial process that starts containers. And now you have control over how containers are started. And this happens usually as root, so you basically have control over the system. So whenever there's an implementation issue in the kernel or in the user space tools that deal with containerization, you can potentially get a security leak. That's why virtual machines are considered, one of the reasons why virtual machines are considered more secure, because you have to specifically make a contact between the virtual machine and the host. Okay, what's the time? Okay, still have some time, that's good. Alright, so user namespaces. Why do I think that's interesting? Because I use too much sudo. Ideally, nowadays, you want to avoid using root permissions wherever possible, because every time you use root permissions, something could go horribly wrong. Like I could screw up my system, or I could run a process that I should not have run as root, or I could delete some files that I shouldn't have deleted, and so on. Also, from a security point of view, if you can avoid becoming root, we can avoid like giving someone root access without wanting to. So that's why user namespaces are interesting. When you create a new user namespace, you can become in this user namespace root. And the isolation of these namespaces here is such that you don't get any more permissions outside of your user namespace. So that's kind of the root of trust and the root of permissions. So unshare -- user -- map root user. I do this without root rights, and now I'm root. But what does it actually mean? This means there is a mapping of the user IDs. I have, outside of the container that I just created, outside of the namespace that I created, I have user ID 1000. Inside of the container, I have user ID 0. So there is a mapping between those two. I can actually take a look at the mapping. If I get my process ID, I can do the following. Cat proc 4150 UID map. This map tells me that the user ID 0 inside of the container is mapped to the user ID 1000 outside of the container. And these two are ranges. In this case, they are ranges of the length 1. So I could also have a range of the length 10, for example. Here, that's the length. And then the user ID 0 to 9 would be mapped to the user IDs 1000 to 1000 through 1009. But if I start this user namespace from an unprivileged user, then the only thing that I can create is essentially this mapping, because I cannot just impersonate other users or get another other user's user ID. So the only thing I can do is I can only map my own user ID to something else. In this case, I mapped it to user ID 0, which is special, which is the root user ID, which gets additional permissions, but only inside of this user namespace, because only inside of this user namespace I'm root. So now, from here on, I can do further things, like I can create a new mount namespace. And now I can basically do the same thing as before. Maybe we cannot call it proc. Let's do a bit more, less confusing. mkdir my container. Mount -- bind container cpvka to my container. And I do a pivot root, so I have to go to my container, and I do a pivot root dot on dot, and I do an exec on busybox sh. So now I did this entire spiel of changing my root directory, but without starting with root permissions. I did this entire thing unprivileged, so you can see I have no usage of sudo in this chain. And I think that is really interesting, because it allows me to do this entire containerization thing without accidentally doing something that I did not want to do, because I only am my unprivileged user the entire time. Something like this. The groups are currently unmapped, most of them, except for my main group. That's the last one, which mapped to ID 0. But I start this entire thing off with, so when to compare this, I start this off with various groups that I'm a member of, like sudo and dip and so on, and they also have their own group IDs, like 4, 24 and so on. But these groups IDs are not mapped inside of the user namespace. There's only a mapping for one group ID, and that's the main group ID of the first group in there, 1000. This main group ID 1000 is mapped to 0, and that's the last entry in here. And the other ones have overflow values, because these things are not mapped inside of the user namespace. Okay, so that is great. Now I can do containers without root. So what would be the next thing to talk about? Yeah, for example, there are some security features that make dealing with these kinds of containers at this level a bit tricky. For example, I cannot mount the proc file system from here. I have already the busybox ls / I already have the folder proc, but if I try to do something like busybox mount -t proc none proc, it will tell me permission denied. Are you root? Yes, I am root, but I still get permission denied. The reason for this is some kind of security feature that I do not quite understand. You have to do this before creating before changing root. So you can only mount the proc file system if a proc file system is currently visible in your mount namespace.
Sounds like it could break assumptions made by programs and create further exploit opportunities.
So I can do this before I do the pivot root thing. I still have access to demonstrate this. I still have access to this proc, right? So while I can still see this, I can actually... Oh, I cannot. Might be that I have to use a PID namespace for this. Not entirely sure. Can I run sudo from here? The point was to avoid this. The order of operations is tricky. I have written it down, that's why. There is sudo, but I'm already root. Yes, but for sudo it's also a process that now runs in this user namespace. It can... What should it switch to? It can only switch to user ID root, no, 0, and that's root, that's already what I am. So let's look into my notes. You can combine these things, so they are built into this unshare tool itself. Documents, containers, CP, there's this read, maybe check an open as read only. And so the order of operations was... I think I have to do this with a new PID namespace, because otherwise I could gain access to other processes that I did not have access before. So from my shell that I have here, I create a new mount namespace. I get out of this mount namespace because it doesn't matter. I unshare -PID -mount here. Okay, yeah. That's PID namespace. That's an interesting quirk of the PID namespace. The process which creates the PID namespace is not yet part of the PID namespace because it still has its old process ID. The first process that is then spawned as a subprocess gets PID number 1. And if this thing exits, then the entire PID namespace disappears because its PID 1 has disappeared. So this is confusing a bit. So I have unshare minus PID, which then starts it execs a shell, execs a bash, and this is not yet part of the PID namespace, and this then does a fork. This thing becomes PID 1, this fork execs, and then the bash tries to fork again, but the PID namespace is gone. So what you do is here, in between, you do fork. With the fork you create a new process, this becomes PID number 1. And then you create PID number 2, and if this exits, the bash does not, or the PID namespace still remains there. This is every time it gets me. So, why don't I have unshare in here? Now I'm confused into what namespace I am. Okay. Minus fork. I know it works. Okay, so cannot allocate memory is misleading. I can allocate memory, you just have to be careful with forking. Okay, so now we should be able to mount minus t proc none on this proc. And now it works. Okay, so for security reasons I have to create first a PID namespace, and then I can mount my proc namespace, and then I can mount minus bind dot slash my container, and then I can go to my container and perform the pivot root. Oh, make sure that proc here contains anything. Yeah. Bind mounts are not transitive. That's also something. Proc. And now I can do the pivot root dot, and then I do the exec busybox sh. Okay, I think we're getting busybox ls proc. Okay, now what we see here is, if you look entirely to the left, there are just two processes. One is the busybox. One is this busybox that's running as shell, and the 18 is this ls command. So I cannot see any other processes now, which is different from what I see essentially when I look at /proc. Okay, so what isolations do we have now? We have a PID namespace isolation, we have a user namespace isolation, and we have a mount namespace isolation. So now we can also get a network namespace isolation if you want. But let me just first step a bit to the side and talk about what these how these namespaces are associated. They are associated with processes. You can see this somewhat in the proc file system. So if I now open this, and now it's getting tricky because I want information about this process which is running on the top. But what process is this? Like, what is its process ID? Its process ID inside of its own namespace is 1, but that's not very useful. I want to know the process ID of this in the root PID namespace. So I do a pgrep for busybox. Okay, it's process ID 4285 in the root process ID namespace. So, and here there is a there should be a namespaces directory somewhere, ns. So this proc is the virtual file system, so I get information now about this process, the process that is running above, the shell is running above. In this ns folder there is information about the namespaces of this process. It's not really very instructive to see this, but we can at least compare it. So what can we compare it against? We can compare it against, for example, no, not like this, we can compare it against ls-l proc self ns. So now I'd like to scroll a bit. I can only scroll down. Okay, now we can compare it more or less directly. What we should be able to see is that the numbers for the PID namespace, the mount namespace, and the user namespace are different. So you can see here this is 37 and this is 94, this is 96 and this is 36, and where's it, mount namespace 95 versus 40. So these two processes live in different namespaces. But I can enter a namespace from a different process. So these things are not isolating in the sense of that I cannot get out, but I can get in from the outside. This is, for example, how Docker exec works. So I can spawn a new process that is also part of one or all of these namespaces. So let's see. I'm not sure if I can do this without root. Enter minus target is 4285 minus user. Yes, minus group. There's a switch that I have now to use because of security reasons. Or I use sudo. I can also always use sudo. minus preserve credentials. Okay, with preserve credentials works. So also without root. And now I'm in the same user namespace as the process on the top. But I don't share any of the other namespaces. I'm still in the root mount namespace and what else? The root PID namespace, for example. So that's not very useful, but I'm root. I'm the same root as the root above. So let's, for example, try to go to the same PID namespace. Hopefully that will work. Yes, this will work. So let's see what you can see under proc. Yeah, that's still the original proc, right? And to see the other proc, we'd have to enter the mount namespace. That's basically where it ends being funny, and just we have this different shell. But we can still do this for instructive minus mount. So now, unfortunately, we cannot run ls. Oh, we can run ls. That's good because there's a bash built-in. Why didn't we enter this? Oh, that's interesting. That's also something I did not observe. But it's root. But the root of the entire mount namespace should be /. Should be have moved. Never mind this. What I wanted to demonstrate, and failed to do so convincingly, is that you can from the outside enter into this process namespace, into the namespaces. Say something like documents. Where did I put it into my container? And then what? Okay. Anyway, what I wanted to point out is that I have seen people put all kinds of tools inside of their container file systems, such that they later have these tools when they enter the container. But on Linux there is not the container, there are namespaces, which means they can enter selectively some namespaces. There are not arbitrary combinations possible, but some combinations are possible. Like you can enter, for example, the PID namespace without entering the mount namespace. And this allows me to have tools outside of the container that I use to inspect the state inside of the container. It's not necessary to put all of your tools inside of the container. There are people, for example, who started SSH servers in a container to SSH then into the container. It's not a virtual machine. You can enter into the namespace from the outside with very lightweight tools. But this also demonstrates like the difference between the VM and namespaces. This thing is fully isolated, and here we have different isolations that I can selectively then enter or not enter. Okay, so unfortunately my demonstration failed of the root. I don't really know why. But okay. So let's see if I have anything else to say about this unprivileged stuff. This you don't need. This is uninteresting. Okay, network namespaces. Yeah, network namespaces are interesting. So network namespaces, as I said, isolate the network devices, the TCP/IP stack, and the firewall rules. So I have a short example here. Normally, when I do network examples, I use Netcat. Netcat is a tool that you can run both in a server and a client mode, and it just sends text messages. So you open a Netcat on one end and Netcat on the other end on ports, and then they can communicate to each other. You just type some text in. This is used for testing mostly nowadays, I guess. The unfortunate part of Netcat is that it does not block the socket. And I want to demonstrate that you can actually block the socket in a network namespace, so I had to write my own Netcat, which is called mycat. So let's get out of this entire namespace thing. Unfortunately, it's not much of a C++ program. It's more of a C program because this just uses basically that's the program. There's not really much more to it. The first part is reading arguments, and then it just does the normal socket thing. So it opens the socket, and then it accepts connections, and when it accepts connection, it just does an echo thing. So whatever it gets, it sends back. It's, I think, not really worth discussing. I did not even use nice C++. I just threw everything into one function just to get this thing done. But hopefully I can compile it. Yes, this thing, I'm not sure how to avoid it, this warning, because it's complaining here about a missing initializer. And if you look at this program, the missing initializer is initializer of this sock address struct. The documentation says there are 3 members. For whatever alignment or so reasons, there is a 4th hidden member. I could now go ahead and just initialize this thing, but it's not documented, it's in implementation detail, so that's why this warning is there. Yeah, but it might be that in another implementation this member is not there. It's not documented that it's there. It's just in... Yes, but I don't want to zero initialize it. I mean, what I can do is I can just zero initialize it, afterwards set the fields, but then it would not be const. I have to run the return to a function, and this is messy. This is a warning. This is a warning. It will still be zero initialized the last member. I just don't know how to really get rid of this warning in a portable way. That's why this warning is there. Okay, so now let's just demonstrate what this thing does. When I run it without any arguments, it listens on the loopback interface and on a random port. To find the port, I can do something like a netstat and strnpl, and then I see in here that my tool here has the process ID 5402, and it's listening on this port. So I can run changed documents, container, cp, vka, one. Sorry for IPv4, I don't know IPv6. What did I do? I use as a client. I forgot what I used as a client. I think I just used Netcat as a client. Alt 1. Oh Jesus. 1 3 8 1 3. Ah yes, I just used Netcat as a client. So mycat is just a server. I didn't implement the client part, using Netcat as a client, which is okay because all I want to do with my mycat program is actually block the socket. That's why I also got this address already in use error when I ran mycat again with the same port number. So it prints some stuff about the connection state, and then I can go back and forth. And what netcat and the bottom does is I can see my own input that I typed here in the terminal, and then I can see the response from the server, and the server just echoes back whatever it got. So that's why you see everything twice here. But it's like a trivial program that I can do. So for the purposes of what do I need for a network? I just need a user. So I'll just leave out the entire mount namespace part because just want to demonstrate the network namespace thing. So what I can do is I can unshare, and I think I need a user namespace for this. Net. This was maybe not the smartest thing. Minus map root user. No, I'm root. Wait, I was root before. I was still in some kind of namespace. Doesn't matter. You can nest namespace. Everything is fine. Okay. So I run mycat. Tell it to listen to the. Oh, we can first demonstrate what we have here. IP link. So I created a new network namespace. And have no network devices except for loopback interface, whereas below in the root network namespace I have two more devices, my Ethernet device and the Wi-Fi device. So this already shows that these two things are really distinct, and the network namespace above is kind of isolated currently. So I can now run mycat on the loopback interface on port whatever 1234. And I can run mycat below also on the same thing. So, and this will work. Why? Because these are two different loopback interfaces. And currently there's no network connection between these two namespaces. Okay, so let's create a connection between these two, because otherwise, well, I can now isolate a program so that it doesn't can call home. And it cannot access the internet, and while it can access all of my files, it still cannot send them to some cloud service. But maybe I want to actually have a service in there running that connects to something. By the way, don't take this as a security feature. There have been demonstrations of side-channel communication, for example on Android, where you have one process which you allow to read your files, and one process which you allow to access the internet. And then they communicate via side channel, for example, via caches. You know, these cache attacks, for example. So cache timings, or what I don't know, how much the CPU has been heated up, or I don't know. Like, isolating things from the internet is hard, and this is only a very insecure way of doing it. Okay, so I want to create now a connection between these things. And in Linux there's fortunately a kernel feature for this, which I will have to quickly draw. So we have two network namespaces. It doesn't really matter that one is currently the root and one is not. This means we have application or process in here, have a process in here and have a process in here. Now, if I want those two processes to communicate via network, I can, for example, have here a virtual network device, and here a virtual network device, and have them linked together. This is called a VF pair, for virtual Ethernet device pair. So when I create a VF pair, I get two devices plus a connection between those two devices. They always come in pairs, so to speak. So the way this is structured is I first create a VF pair in one network namespace. Then I take one and move it to one network namespace, like here, for example. And then I have like this connection. And then I take potentially the other one and move it to the other network namespace, like so. And then I have this setup. I still do not have quite connectivity, but I still have, at least I have the connection. This is like a physical cable. Now I need the configuration for this. And for configuration, I normally just do a static configuration. I just write in there an IP address, something like this. And here on the other end, I say something else. And I say that they're in the same network. And that is sufficient. Because if they're the same network, I don't need a route. I need routes later. So, the one unfortunate part about this entire thing is that I cannot move one link or one end of the VF pair without root permissions. At least I do not know how. And at least not if it concerns the root network namespace. So, if one of these network namespace here is the root network namespace, which I will do now for purposes that become clear later, for internet connectivity later, modifying this root network namespace requires root rights. And while I want to do everything here without root, I have no way of doing it. I think no one knows how to do this. There are alternative solutions to this, but this is a simple solution. So I start off as root on the, let's do it like this, ps1 equals container dollar. And let's clear this, and say ps1 sudo minus I. Okay, say ps1 equals root, and clear this. So let's just make sure that we are in the right namespaces. Okay, containers are isolated and root is in the root network namespace. So now, what was it? IP link at type VF. Now the name for this thing is container. And then it's the thing peer name root. Okay, I need to look it up again. IP VF IP link at, okay, IP link at container. This is killing me. Okay, just the order of arguments, which was wrong. So if I now show again what kind of interfaces I have now these two new interfaces here, and these are the VF pair. You can see this. One end of the pair, the other end of the pair, and here it's just reversed. And these are connected with this virtual cable, so to speak. So now I can take one of them, but first this is probably in a PID namespace. No, it's not. That's good. IP link. What was it? Set def. Set def container. Was it NS? NetNS 4530. So now I'm moving one of these VF pairs into the network namespace identified by the process ID. Now I should have her here. Okay, now I have the other end of the the other end of the VF pair is now inside of the container. Okay, now I do this IP address at 10.0.0.2/24 def container, and I have configured it. IP address at def root 10.0.0.124 def root. Okay, so IP link set up def root and IP link set up def container. Okay, I would like to demonstrate something with a ping now, but ping in a user namespace I think does not work. I forgot the reason. I think it's also against security. But I can run mycat. I run it on port 1234. Oh, sorry, that's not what I wanted to do. I wanted to 10.0.0.2. So now do a netcat. Oh, there'll probably be the firewall in the way, but we'll see about this soon. 10.0.0.2 1234. Ah, okay, no firewall in the way, that's good. So what do I have here? I have now mycat running inside of the network namespace, netcat running inside of the root network namespace. And they can communicate via this VF pair. And I believe Docker is also using the same technology. So the same VF pairs. Okay, now it comes essentially down to ordinary Linux networking, how to get internet access from the container. So I have now demonstrate this with a different setup. So let's see, I have a root network namespace and I have a network namespace inside. I have the VF pair. There's another VF. And this is the root netns. And this is the some netS. So, how do I get internet access from here? Ordinary Linux networking? There are multiple ways to do it. Sorry? Just route it through. Yes, this would be one way to do it. How would you do it? Like in broad strokes?
On the inside, and say default route. And
Okay.
on some router outside of your computer, set a route to that network through your host.
If you want to have outside connections being able to talk to this thing. Yeah. Yes. So this is just ordinary Linux networking, so the people who are familiar with this will probably understand what I'm doing here. The easiest way to get internet access is to define a default route. What this means is there is a set of routes. Currently I can show this, but it's not very interesting. So IP route shows the routes, and there's only one route because I set up an IP address with a network mask. This is /24. I cannot point to it even, it's too high up. All IP addresses in this network are being routed via this virtual network interface that I created, this container thing, this thing here. Because I set up here an IP address, there's an implicitly created route for it. But if I wanted to reach another IP address like 1111 or 8888, there is no route for it. There's no way, for the kernel, there's no knowledge about how to get the packet to this IP address. A default route matches everything else that is not called by other routes. So whenever no route matches, the default route is used. And for default route, also have to specify which device to use. So IP route at default via container. What is it? Wait. Ah, yeah, okay. Via 10.0.0. No. My own IP is. I have to specify where it's routed to, not where I'm routing it from. Yeah. Okay.
You have to specify the next hop.
Yeah, I have to specify exactly. We have to specify the next hop. Okay, now the packet can go from the process to this pair, end of the pair. From the process to this end of the pair to this thing. But here it's basically lost because there's currently no configuration of what happens when a packet arrives here with the destination IP address that is not for this machine. So what I can do now is I can can tell the kernel to behave like a router for this interface, which means that any package that arrives here that is not for any of the interfaces here will be routed via the normal routing system of this machine. And here it will arrive also at the default route, and then it's being routed out to the internet. So, in order to do this, I just have to set one kernel parameter, and I do it the easy way, which is the insecure way, to proc sys net conf IPv4 conf all forwarding. So now I told the kernel to behave like a router for all interfaces. But it is still not quite enough. There's one last step to take, and the one last step is to masquerade. So now the package can essentially leave from this VF to currently my Wi-Fi is connected to the internet. So the kernel will take the package here, which arrives, for example, for destination IP address 1111. It realizes, okay, this is none of my interfaces. Then I route it via my default route, and my default route is currently set up to route via my Wi-Fi to wherever this thing is. So it will go here, it will go there, out, but it still has as its source IP address the source IP address which it was sent from. So there's no way back. This is why I have now to deal with ITV tables. Minus t nut minus append. This is post routing minus. There's a jump to masquerade, and there's I think a from address. It's an out interface. Out interface, and this is P12S0. Okay, and this thing sets up network address translation, which is the last missing piece of it. Not quite the last piece, because I should be able to now reach machines via IP, but not via hostname. Except, do I have it set up here? etc resolve.conf. Yeah. The problem that I now have is that my Linux system is set up in a way that it has a proxy for the domain name system. So whenever there is a program which wants to reach a server, for example Heise or Google or the web page of the KIT, first step is or not the first step, one of the first steps is network name resolution. So I need to resolve that name to an IP address. And the way it's implemented here is via a proxy. So there's a program running on this machine which listens here on this loopback interface 107.0.0.1, which caches, for example, the incoming request, so that two programs that query for the same name don't have to send out two packets to the actual name server. The problem with this is this name server runs in the root network namespace, and it's not reachable from inside of this network namespace. So I would have to override the resolve conf. Can I do this? Normally when you do containers, what you do is you combine the network namespace with a mount namespace in a different root, so the container has control over the resolve configuration. And then you can just overwrite this file. But I choose not to do so here, which was a mistake. Let's just fix this. So I'll do the entire thing again. Pit minus mount. Okay, so now combine the entire thing that we did before with pivot root and so on in one line in unshare, because unshare has all of these things built in. And now I can do a... Oh no, I can't do this. First I have to... If I wanted to run this, I would run into the problem that my own program... oh, I cannot even use my own program, this sucks. I have to use some other container. Let's use the Debian container. Sudo unshare minus net minus root ubuntu. Yeah, I'm still in some namespace. Okay. So sudo unshare minus root minus net minus root equals ubuntu. That looks okay. Seems okay. That looks better because it's different from the thing that is inside of here. Yeah, so it's different. Okay, so I have now switched to a container which contains an entire Ubuntu, so that I have the tools that I need. What I just do is I will write this with a name server 1.1.1.1 to etc. Thanks. I was confused those. So I have to do this entire shenanigans again, unfortunately. IP link yeah. Yes, because I think they only come in pairs, so if you remove one pair, the entire thing is destroyed. It could be restored to the original, but you know, it could be differently configured. I think that's the entire problem. So I have to use root here because in any way how to configure this, one of the ends of the VF pair needs to end up in the root network namespace. And that's why I have to be root at some point. I have 5177. Set the network namespace for this device. Then I do the other IP other at 10.0.0.2/24.2 dev container. So IP link set up dev container. IP link set up dev root. Okay, now I hope that I didn't forget anything and this should work. Okay, this should... Sorry? Thanks. IP route at default via 10.0.0.1. Ha! Success! It took a while. But yes, so what we have to do, again to recap, first we have to create a connection between the network namespace and the root network namespace. You do this by using a VF pair. Then we have to set up the routes. So we have to set up first that process inside of this network namespace actually use this link to route traffic that is for outside, for internet. So then at this outside in the root network namespace, we actually have to allow that packets which arrive here for other IP addresses are being routed via the routing rules inside of root here. And finally, we have to set up network address translation such that the back traffic actually can make it back. And now we have internet from the container. And via similar tools, we can create network between two containers, for example. But what often happens is, for example, in the context of Kubernetes, you have pods, and a pod. Sorry, I thought I still had the namespaces here. A pod is a network namespace, and a pod can run containers, and containers translate more or less to mount namespaces. So in there, you have one example of not a full encapsulation. By being a network namespace, all the containers inside of a pod can communicate via the loopback interface. Because the loopback interface is the same loopback interface for all of these processes. But by having a different mount namespace for each of these containers, they can have complete separate file systems. So I can have, on the one hand, a glibc-based Nginx, on the other hand, a Musel-based Apache, if that even works. I don't know. So different versions of glib, different implementations of this C standard library, for example, or I can have two Apaches in different versions next to each other, different containers, because the file systems are still separate. It's just that their network is shared.
You can do all that without any namespaces at all.
Yes, but then you have to configure them. So, how are these network namespaces used by Docker then? There is obviously the port forwarding. So if you have used Docker, you have seen that what they do often is they map a port from inside of the network namespace to another port, or the same port, on the host. This also works via these IP table rules. So these IP table rules are, I think they originate from being a firewall, but they allow you to rewrite and reroute traffic. So you can take traffic that arrives here and reroute it to a different port outside, or the other way around. You can take traffic that arrives at the port here and route it to this specific VF on a specific port.
The destination gets rewritten to the address inside, and
Yes.
that gets routed the normal way.
Yeah. But in the end, what you specify is that essentially it goes inside of this network namespace. Okay. Now, if you look at tools like Podman, which try to be completely rootless, they have a slightly different solution. As I said here, the problem is that in the end, to route traffic to this root network namespace, you need to change something here. Like, for example, you need to set up this thing, this end of the VF pair. So for this, you have to be root at some point. The alternative to this is to use, to not use these virtual network devices, or not a VF pair. What rootless networking, so networking without privileged users, does is it creates a virtual device in here called a tab device or TAN device. They're similar. This is a virtual interface device whose other end is a file descriptor. And now you put this file descriptor outside of the network namespace. Well, this isn't really a network namespace, a file descriptor, but you put it in a place where an application can read it that does not live in the same network namespace. And then you have a process here. Well, a process here, so there's a process A, which writes to this tab interface as a network interface, so it does normal network communication with this thing. And there is a process B, which reads from this file descriptor and then has a TCP IP stack inside of here and then performs normal network operations to the actual network interfaces here, for example, Wi-Fi. And because a normal process on the host can do normal network operations, you don't need root for this thing. It just needs access to this file descriptor. Because you create it, you can have access to this file descriptor. You need to create a tab device in here, but you can do this in the context of the user namespace here. So there's a user namespace. Inside of this user namespace, you are privileged. You can create this tab device. And this process can also be unprivileged and just talk to this tab device. So it's somehow clear. It's maybe a bit confusing.
Can you actually create another temp device on the same file descriptor and thereby use the TCP/IP stack of the current?
Maybe, but you would need root permissions in the root network namespace for this. So
But you could connect two sub-network namespaces with temp devices.
yeah, but you can also use VF pairs for this probably. Yeah. So what is the disadvantage of this? The obvious disadvantage is you have a TCP/IP stack in user space here. And they claim that this is the reason why it has reduced performance. Not entirely sure if having a TCP/IP stack in user space always means having less performance, or if the implementation is not so great. But currently, the restriction is one of the restrictions of user space networking is that there are performance downsides to it. Another downside to it is that since this here is an unprivileged process, otherwise there would be no point in this exercise, you are restricted from binding to certain ports. That's a security feature of Linux. So normally the lower, I don't know, 1024 ports or so are restricted, and only privileged processes get access to them. And this is if this is your configuration and this is an unprivileged process, you cannot get access to this low 1024 ports. So no HTTP server, for example, via this thing. What you can do is you can again restrict your usage of root and, for example, just create an IP tables rule. So that then reroutes the traffic from whatever port this thing runs on, say 8080, to port 80. And because manipulation of these IP tables rules is simpler than having an entire IP TCP/IP stack, maybe it's like less problematic enough to manage this via setuid binary. So setuid binaries are the main protective feature or the main user changing feature of Unix. If you, for example, run su, what happens is su has a flag that says if you run su, the process is run as uid 0, as root. And then su protects itself against you abusing it. Or sudo in the same way. So sudo asks you essentially for a password and then checks that that password is correct and then lets you change users. But su itself runs as root. There has been, for example, recently a security issue with sudo. And the problems come of this, like the more complex these programs get, the more likely is that they contain some kind of security issue, and if they do, then you can get immediately root access because they start as a root. But you see these kinds of setuid processes also here in user space containerization. For example, in the mapping of user IDs. Like I told you before, when you normally use an unprivileged user and start a user namespace, all you can do is map your own user to a different ID inside of the user namespace, because you cannot impersonate any other users. But sometimes you want to run different processes under different users inside of a container. For example, if it's a bigger container which contains like half an operating system, maybe you want 2 or 3 users inside of there. Then you need root privileges to map not just your one user ID to the network to the user namespace, but several others also. So, for example, you want to map your own user ID, which is maybe 1000, on the root user namespace. You want to map this to 0, and then you want to map like 100,001 to user ID 10, and 2 to 12, and so on. And this gives you here then additional users that you can use inside of your container. And for this purpose, for example, there exists a setuid binary, which is called, I forgot the name, but that's the configuration file. That's the it's etc subusers, and it's used by, I forgot the name for it, but you will find it. And there are similarly tools that deal with some of the restrictions by using setuid binaries. What this how this thing works is that there's a configuration file, etc subusers, and it tells this tool which users you are allowed to use. So inside of here, it tells something like, okay, the user with the ID 1000 is allowed to use the user IDs 100,000 to 100,000 and I don't know 55 from the root user namespace inside of the namespace that it creates. And then of course you need to restrict access to this file, because if anyone can write to this, then anyone can create any mappings in here and map the root user of or any users into their own user namespace and then make use of them. So setuid binaries are nice to have. They can allow you additional functionality that you would otherwise not gain if you have an unprivileged user, but you need to consider their security implications always. That opens an interesting question. So what happens if you override the dynamic linker via a bind mount? Yeah, but you open the user namespace, you are root. Open the user namespace and the mount namespace.
Root in the namespace and
Then you
whatever
set
you
your
run.
Then the setuid run also root inside of namespace. Oh, true. So that's probably one of the reasons why I cannot create a mount namespace without creating a user namespace. Okay, so that's about it with networking. Not sure, it's probably already late. I have more to talk about, but yeah. So, questions at this point. Otherwise I might just change topic slightly and tell something about why I use containerization, or the fun things that I do with containerization. The profile system, I don't know. This is not what you normally use. Normally you would use higher level tools like Podman or Docker or Alexi, which all do these kinds of things internally. But I found it very instructive to see the different parts that are involved, for example, to understand what Docker exec can do and cannot do. Unprivileged network, compiling a static executable. Yeah, that is something that I would like to talk about. What you do with Docker normally is a very simple way to build containers, but it also can be somewhat dangerous. I think one of the main reasons, or I believe, I do not know, I believe that one of the main reasons why Docker is popular is because it makes it extremely simple to build containers. You take something that you're normally already somewhat familiar with, for example, you take a Debian, and then you run a package manager, which you're normally also somewhat familiar with if you're using Linux, to install additional packages. And then finally you put your own application in there. Maybe you don't even need your own application, you just use something from the repositories. This results in containers that are bigger than they would need to be, because you start off with something more than you need to. You don't need to ship an entire operating system and package manager if all what you do is want to run one service. But it's one of the most easiest way I have ever seen anything set up, just to be able to type, okay, from Ubuntu, run apt-get update and install this thing, and then you're done. What you also have to be aware of is that this makes you dependent on the package repositories and on Docker Hub itself. And in a corporate environment this might not be viable, because you might not want to rely on those things. They could be down at some given point. There are no guarantees for you as a mere user who doesn't pay for these services that Debian keeps up their repositories, or Debian keeps up their old repositories if you need old builds. So having
had problems with a Debian repository that was down just last week.
Yes. So one of the things that you have to be careful with is you have to always keep your stuff up to date. Because if you don't, the old repositories will go offline at some point, and then you will have trouble. You will have trouble. You will not be able to refer to all Debian stuff anymore, because at some point it's gone. Like in 3 years, they might not have the old release repositories up anymore. So you have to rebuild your stuff again and again. You have to keep it up to date if you want to rely on these external stuff. Otherwise, you have to start mirroring things. You have to mirror the repositories, you have to mirror images from Docker Hub, and so on. The alternative to building things from this package manager point of view is to build it by assembling things. Then you have exact control over what goes in your container, but you also have the trouble of having to put everything you want inside of the container. This is where static executables are quite interesting because they have very little dependencies. With C++, this is somewhat of an issue because of the licenses of the stuff involved. So if you're in a corporate environment where you cannot just put stuff under GPL, you cannot easily statically link to these binaries. You can easily statically link to glibc. Wait, you can easily link to glibc and to libstd C++, but static linking to them violates the GPL license if you don't release the source code. Statically.
Static linking is allowed.
So my understanding.
If you are going to pass the binary on, then
Okay, yeah, so yeah, so cloud service providers don't have this issue. If you have software as a service, you can basically screw everyone.
the software is HTML.
Yeah, there are new software licenses which are against these kinds of things. Yeah, but yeah, if you run some kind of on-premise thing where you release your images, the container images, then you have to take care. Like you cannot easily use static linking with GNU stuff. It might. I have no idea. I believe that at least the client stuff is BSD licensed. So if you want really to statically link and everyone advises you against it, in C++ at least,
But I think there's no Clang or LLVM C library, but just a C++.
there's a C++ library, that's true. But who wants to use the C library? Just kidding. Everyone has to use the C library.
C++ library probably wants to use it.
Yes. That is more interesting for languages like Go, which have a background of being statically linkable. Nowadays, I hear that it's more complicated to do it, but that's one thing you should think about. Like, do you maybe want to statically link to just reduce the size of the, not the size, but the complexity of your container image? I don't think anyone does it, to be honest. I think everyone's using package managers. Like, probably the vast amount of people, because it's just easier, less hassle. You don't have to deal with some kind of things. Okay, what else? Yeah, security issues. If you have a container and you ship this, or if you can then run it as a software as a service, what do you have to actually monitor for security issues? Does anyone know which part of the container image is used and which part is not? This is a very tough question. How do you analyze this even? Like, how do you start analyzing this? Like, do you do runtime analysis and live with the fact that there are code paths that you might not have checked? Do you try to use a static analysis, but then do you find anything? Like, can you do this? Yeah, the problem is not that your application is exploited. The problem is that your application is exploited via a library that is in there, or via a binary that is in there. So if there's a security issue in, I don't know, some kind of bash, for example, do you know if this is used in your container or not? It's in there, the binary is in there. Yeah, libjpeg. So what you do then normally is you scan the entire container and see if there are any security issues in there. And of course you will find more than if your container is minimal. If you have set it up with a package manager, there's lots of stuff in there. So containers really lend itself to automatic build systems and full automatic build systems, such that if there is a new version and you want to keep up to date, you can just trigger it automatically, or you can trigger it by just push of one button. And similarly, if there's a security issue, you update something and you build the entire stack. I'm not that familiar with embedded devices. Yeah. Interestingly, if you look at Docker specifically, Docker works by building images in layers. And if you have a layer that removes files, they're just marked as removed in a new layer. They are not gone from the entire package. This is one of the reasons why they, for example, tell you if you want to run your package manager and it updates the list of packages, you should in the same line also remove these lists again. So this lists are kind of the meta information about which packages are available. And they tell you in the best practices, if you run apt update to fetch this list, in the same line you should also remove rm and -rf dash varlib apt list star to remove this entire thing again. Because once you end this line, you commit a layer in the image, and this is immutable. You can then in the next line remove it, but it's just then a new layer in which it marks these files as being removed. So if you want to build a minimal image, you cannot just build it with steps in Docker, because, well, the file system you end up with is minimal. So from a security point of view, it's better, but the container size is still big. So maybe you build this entire thing and then you copy it over to another container, like with this multi-step builds, for example, in Docker. But yeah, I don't have many answers. This is not my main focus. It's just the questions that I came up with in the last couple of years. So yes, yeah, there are many alternatives. I think just that Docker is very popular because it's easy to do things, and you don't have to change your application. It's relatively simple to take your existing legacy application from like 10 or 20 years ago, which you already have an installation system for it. The installation system usually is based upon a Linux distribution or several Linux distributions. You just take one of them, install the same packages, repeat the same steps that you did in your whatever Ansible or whatever you used before, put this into a Docker file, and then you end up with a container. I think that's one of the main reasons why it's so widespread. And if you talk about changing to WASM, yes, might be a good idea, but for most people this would involve too much work. For now, yes. These are the creative uses. There's some things. Yeah, why I'm using containerization. I'm using containerization because of these reasons, and also one reason that is not on that list. That one reason which is not on that list is a couple of years ago I started building open source stuff from the internet, mostly Clang. And it always annoyed me that I have to install dozens of packages until this thing is finally working, and then I switch to a different computer and I have to repeat this entire thing over again. And so I started using a container. Just in the container I installed all the packages. And because I use Docker to create the container, I have to write down how to install those packages. And it becomes automatically repeatable and independent of the operating system which I'm running. Because Docker is designed in a way that it restricts you what you have inside the container. That's why when you do a Docker build, for example, you only get as an input to your Docker file all the stuff that is inside of the folder or below folders. That's how they make sure essentially that you're not dependent on any of the system stuff. I expanded on this then because I don't just want to compile Clang inside of a container, I also want to run Clang inside of a container. And by the way, I want to cache the intermediate results so I don't have to compile Clang all over again. And Docker offers this volume mount thing, which is just a bind mount. We've seen this before, right? So we have this isolation of a mount namespace, and inside we change the root, but we can have bind mounts which refer to outside of this root. And this is how you can map folders from your host inside of the into the container. And I'm doing this to restrict the inputs and outputs of the tool that I'm running inside of a container. For example, for a build system, my output is usually the installation directory and the cache path where all the object files are compiled into. And the input is my Git repository. And the container itself is immutable. It just contains the build system. I check out a new version of the Git repository, check out a new branch. The container stays the same. It just contains the build system. I run the container again. It takes as an input via a bind mount, the Git repository, which means it has not to be copied in. It's just mounted inside. And then it creates new object files and new installation to the outside. And I basically do this for all open source tools now. If I'm not entirely sure that I want to install them on a system, or even if I think they're good and useful, but I just run them inside of a container so that I don't have to modify my system. This also makes it easy to switch to a new system, because all I have to do is I have to configure some stuff on the host, and the rest is done by Docker containers. Yes, possible, but how do you set up the container for it? Yes, you can move the entire file system. So systemd nspawn is another containerization tool, like Podman or Docker. What I don't like about it is that apparently it does not currently work without privileges. So, and it has specific support for systemd, so that you can run systemd inside of the container, that you link somehow your systemd from outside to inside. I don't understand how it works. Systemd is magic. You can use that, but my point is that I don't want to carry around files. Instead, I commit Docker files into Git repositories. So the code that I produce is minimal, and I restore. Yes, but that's not the point. The point you can use the Docker file system with Podman without privileges. The point I wanted to make is that what I produce is just installation steps, and when I carry onto a new system, I just get these new installation steps and restore the entire state there, which takes some time to compile and so on, but the stuff that I transport is minimal. And I don't have to set up the entire system here and there and overall, and just have containers for most of the stuff. So here are reasons why I'm using container in build infrastructure. I was previously maintaining a Jenkins with lots of workers and lots of people using those workers, and they did all kinds of stuff to those workers. So there were orphan processes running around. These orphan processes had then open files, so they consumed not just RAM but also file system space. There were leftover Docker containers which were not properly shut down. There were Docker images which were not cleaned up, so which consumed the disk space. Disk space was also consumed by people writing into their workspace, which is the one folder where you should actually write if you do a job in Jenkins. But they also wrote to tempfs, and they wrote to the home directory because you can. And this is so messy that the workers went down after a while, because they're just overloaded either by RAM or by disk or by process IDs or whatever. Yeah, it's crazy. We were already switching to containers, but I kept them alive by having a cleanup script. The problem with this cleanup script is you have to explicitly specify what you want to clean up, and you don't want to mess with the currently running jobs. So you have to wait until the current jobs are over, and then take this thing offline, and then do the cleanup, and then take it online again. You can imagine the mess this thing is. So with containers you can avoid all of these problems, because you can design them in a way that they remove all the stuff after your work is done. All the processes will be gone, all the disk space will be freed, no RAM will be consumed, and they cannot write to arbitrary directories, they can just write to the container. I don't know about Flatpak. What I've learned recently is that systemd has support for containerization, because of course systemd has support for it. Which means you can use containerization without any of the containerization tools. You can just use the isolating parts of it. In a systemd is the manager for services on most modern Linux distributions, and it's also lots of other things. But for services, you can use systemd now and tell the services that they only have access, for example, to specific folders, that they have their own network namespace, that they have their own whatever namespace, that they are not allowed to use certain... That they have no PID namespace, or it's not supported, that they have a different... yeah. Which might make sense in the context of systemd. Anyway, you can restrict the service. You can even specify it shall run in a file system jail, like this mount namespace with the switch root that we saw. And you can also restrict other resources, like tell the service you're only allowed to use 50% of one CPU or something like this. So if you want an integration of a service into your system, for example, for upgrade purposes. So if you're a maintainer of Debian, for example, and you want the SSH server to be integrated in the rest of the system and not to run into a separate container that is then maintained by whatever Docker or so. If you want really the best part of the system, you can still use these features, for example, via systemd to isolate the process and improve the security. Or perceived improving of security. It's like you can restrict certain things so that you hopefully are more secure. For SSH, it does, yeah, it might not make sense, but there are other services, I don't know, maybe the DHCP services or something like this. But yeah, so, well, we are 10, so should almost end this, mentioning some creative uses, which is like, okay, we're now through the container part of the concepts part of the talk. Now the other part is 2 minutes. I could show them, but don't think I have enough time. So this thing here, I brought this here because it's actually not just a keyboard, but also the device that you can program, because it's open source hardware and open source firmware and everything. But no, QPK, I forgot. I think it's called QPK. The point was, it's some arbitrary software that you download from some GitHub stuff. And I don't know where this thing comes from. I have not reviewed the entirety of the code because it's just too much. So for the Linux kernel, at least, I can be relatively certain that there have enough eyes looked on this. For some weird stuff that I get off some GitHub thing, like what is my reason to trust them? So at least I can run them inside of a container to somewhat restrict what they can do. And here I have to give them access to this device so they're able to flash it, for example. But I can set up a container in the way that they only have access to this device and to nothing else. So even if I even if I run them as root, they're still not able to flash like my notebook. They're only able to flash my my keyboard here. The other part of this is obviously there's a firmware that has to be built, so we have a build system again, and this is also containerized. So I containerize the build system, the firmware building. So the output of this then is the firmware, and then I have the flashing program whose input is the firmware and who's connected to my keyboard here. So LLVM, I mentioned this before, like Clang builds. Rustbox did just the same thing. For every tool that I now do, I build a container and then build it inside of there. Spice, Tiger, VNC, and XRDP are interesting. These are remote desktop solutions. And at work, I have a /15, which, as if you know /, it does not have that many packages, and they're not that modern because it's enterprisey, so you get old versions with long-term support. But if I want to run a new version of an application, what do? I can compile it from source or just use another operating system, right? Just take a Docker container, like from Ubuntu, the latest one, install the package, and I have a new package. Doesn't work if your kernel is too old, that's true. But in these cases... Yeah, so one of the parts of this containerization is your kernel has to support the most recent stuff that any of your containers wants to run. Yeah. And you have no dev console and no dev TTY. Okay. So, in the case of these remote desktop stuff, you have to understand one tiny bit about how the windowing system works, or the entire graphics output thing works. So on Linux you have an application, and the application looks into an environment variable called display, and this tells it then where the X socket is. So there's a socket which is either a file or just really a network socket. In this case it's a file somewhere, so this application sends its commands to this socket. And there is another end of the socket which is the X server. So what the remote desktop things do, they have plugins in here or whatever things, they have integrated them somehow in the X server, and then basically translate from this X protocol to some other protocol, like for example VNC. So I have a VNC server here. So there. So there. So this is one application here. So what I did then is I containerized this thing to get a recent version without having to install anything on my system. I bind mount this file, so I have access to the outside. So I created this file on the outside, then bind mounted it inside. And then I've port forwarded the VNC server port to my host. So now I can connect here to the host. On the host, it goes via port forwarding to VNC server here. And then I can display the graphics here and run an application on the same machine which talks to this thing. It is not new, it's not from me, it's just easy to do. I mean, easy to do, it's neat to do, and you can essentially put your entire graphics inside of a container. The same thing I did for Spice, which is originally written for virtual machines, but it works also via sockets, so why shouldn't you send it over a network? And RDP, which is the remote desktop protocol from Microsoft. So basically you can then have this RDP, so you have an RDP server here. You can take even the original Microsoft remote desktop application and let it display your Linux applications on the machine. So there are people who even take this further then and containerize every single application that they have on their machine, especially when it comes to graphical applications, because why not? Yeah, the last thing here is containerize, and this has something to do with how dynamic linking works on Linux. So if you have a trivial program, normally a trivial C++ or C program, it's normally not statically linked. So it normally depends on a bunch of shared libraries, and those shared libraries depend on other shared libraries, and so on and so forth. And what Containerize does is it gets this entire list, gets the paths of these, and creates a folder which contains them at the right places. Oh, sorry, that's not entirely true. What it does is it gets the list of all shared libraries via this LED tool, and then copies them into a folder under one specific path, contains the executable which you run this program. So the input to this Containerize tool is an executable. It takes this executable, puts it into a folder. Takes all the dependencies, all the dependent shared libraries it can find, also puts it into the same folder in a certain path. Then takes the dynamic linker, also puts it into this container, and into this folder. And then you can build a container out of this, like for example with Docker. It rewrites our path. So the reason why you have to do it, like if you have to include the dynamic linker, is the way dynamically linked executables are started. Dynamic executables contain an interpreter flag that is read by the kernel, and it starts then the interpreter instead of starting the executable. The interpreter is the dynamic linker. The dynamic linker then loads the executable and all the dependencies that are directly written into, like, that are mentioned essentially for the executable. So in a container you need the dynamic linker, the executable, and all the dependencies, and that's what this tool finds in a very simple way. It's not sophisticated or anything, but it's sufficient for simple binaries to create a minimal container. If you, for example, have a test program that you compiled in your own machine and just want to transport it to some other machine, for another colleague, for example, they might have a different operating system with a different dynamic linker, or they might have different different version of system libraries. With this tool, you pack everything together and can ship it somewhere else, and it will run the same way, except that the kernel is different, but that's normally not an issue. This is also not super sophisticated. There are better tools from other people. I just wrote this in like 20 lines of bash. Yeah, as I said, like none of these things are extremely exciting. But it might give you some ideas of what can be done, or like at least what I'm doing with containerization, besides productively shipping containers and using them in continuous integration. This works via layers. So Docker knows about these layers, and if you upload a container image, you check between the server and your local system which layers are already there. The same for downloading. And you only upload or download the layers that are not existing on the corresponding end. So when you execute a Docker container, it builds up a layered file system. So it has these layers, these live in different places as archives normally, and then it builds up a file system view on these layers. So we view all these, yes, if we have multiple layers, yes. The order is important. Like you should put the most common libraries in the root layer, because the root layer was shared between all of them. And if you put them into a lower layer, then you cannot share. Yes. And this is also a reason, I think, one of the reasons why multiple inheritance doesn't work in Docker. Because what do you do if you have a conflict? Nope. It's stupid. It's totally stupid. It's like 20 lines of bash. Yes. So plugins are completely ignored by this tool. It's just that I needed something quickly, and I wanted to demonstrate that you can build a minimal container. That's how you build a minimal container for simple executable. All right. Is there something to say about virtualization? No. As you can see here, you can interface with virtualization similarly easily as you can interface with containerization. So these are commands to run virtual machines here on this above, which is also not that complicated. Yes, this is completely rootless. You would need more permissions if you want to accelerate this with KVM, which you normally want to. But then you can also be in the KVM group. I do not know what this means, to be honest, from a security point of view. It's bad to be in a Docker group. Because when you are in a Docker group, you have access to the Docker socket, and the Docker daemon runs as root. Now you can spawn a container, privileged, and bind mount basically any folder from your system into the container. And then you have root access to those folders. So if you are in a Docker group, you might as well have password as sudo. Yeah, everyone I know basically puts themselves in a Docker group because no one wants to type sudo docker something and then input their password. But there are people who have granted access to other servers, so have granted other people access to their servers. No, you don't get root permissions, but I will put you in a Docker group so you can use Docker. Regarding Docker socket, what you can also do is you can mount the Docker socket into your Docker container. It's a file, so you can use a bind mount, and then inside of the container you can access the Docker host of the system to spawn more containers, for example, or to get root access on the host. So with the Docker socket you have to be careful, and with the Docker group you also have to be careful. You can easily get a security hole there. Alright, questions? More? Everyone tired? Good.
Oh, thanks a lot. Really a lot of information.
Yeah.
The recording worked, so I can.
Yeah, the problem is recording. I have no slides. Like, what should I share with the recording? So,
I mean, yeah.
I mean, I can share this. Yeah.
I mean, the
Hopefully.
was recorded, so
The screen was recorded. Oh, okay, good. There was no passwords on there. Good.
thanks.
Thank you very much. By the way, was this kind of format okay? I was focusing too much on making unprivileged containers work to actually make slides, so it was a bit unstructured. Okay, because like we are now half, so the other half that went was not accepting this format. I have more to talk about.
Next time.
Yeah, but this was already pretty stressful to prepare this because I did not know about namespace or unprivileged containers before. I did a talk where I used root and also unshare with as root at SAP. And at the end, someone told me, but you know, nowadays everything moves towards unprivileged containers. So why didn't you use unprivileged containers? And I was like, because I don't know about them. Like, you can have unprivileged containers? Yes, you can have unprivileged containers. Now I know how. At least I know somewhat how, not fully yet, as you have seen, for example, from the